Hi, good morning everyone. I am K. Narsimurthy. I am presently working in Government First Aid Women's College, Tumkur, as an assistant professor in the Department of Physics. I am going to present a video in the subject physics. This is my 49th video, 49th session for the second semester BSc students of Tumkur University. So I have finished 3 units, 45 videos are over, 45 videos I have presented, 3 units I have finished with these 45 videos, including all the problems, numericals. In the first 15 session, I have presented the electrostatics and a bit of vectors. In the second unit, I have completely, in my video, I have presented the magnetostatics and the numericals. And in the third unit and third 15 videos, I have presented the subject of magnetic materials along with the problems. Right. So in the next fourth unit, this is the last unit. Last unit starts from the 45th session, 46th session in fact. So this is the fourth video in the last unit. Okay. Right. So in this I am discussing the transient current. In the transient current, in the previous videos I have seen the growth of charge in a CR circuit and decay of charge in the CR circuit. Both growth and decay of charge in the CR circuit we have seen in a CR circuit. Whereas when we come to the LR circuit, we have seen a growth and decay of current in the LR circuit. Along with that, I have discussed about the time constant with the help of a graph. Right, those two things are over. CR circuit and LR circuits are over. They are very important derivations in fact for the exam. And now I am presenting the topic LCR circuit. Now, without going to the charging of LCR circuit, I am going directly to the discharging in this LCR circuit, because the charging of LCR circuit was not in the syllabus. It is not kept in the syllabus. Previously in your old syllabus, it was there, that the charging of LCR circuit was there. Now the board of examiners have recommended, board of studies have recommended that is a too lengthy and a little complicated derivation. So it has been removed from your syllabus. Now you have only the discharging of LR circuit in your syllabus. So I'll go directly to the point which is present in the syllabus, that is the discharging of LCR circuit. Right, we have 3 components here. Resistor R and the inductor L is connected in parallel with the capacitor C, and this entire setup is connected in series with the battery with plug key, along with the plug key. Okay, this is a special type of plug key. When plug key is pressed, the condenser will get charged, because a lower circuit is completed, a capacitor and a battery. This lower circuit is completed, so the current flows to the charge will flows to the capacitor, and capacitor will get charged. Then when plug key is released, it contact with the upper part and this upper circuit is closed. Now the capacitor, which is completely charged, will get discharged through the resistor. Okay, the first condenser is charged to a maximum value by pressing the key, and then it is allowed to discharge through an inductor and resistor by releasing the key. And let E be the EMF of the battery and I be the instantaneous value of the current. At any point of time t, if I look at the current which is flowing in a circuit while discharging, be careful, I am not focusing on the charging of LCR circuit. I am doing charging because after doing charging only you can discharge the capacitor. Without charging the capacitor, you cannot discharge the capacitor. So first you need to charge the capacitor, then only you look for discharge of capacitor. So my point of focus is about the discharge of capacitor through an inductor and the resistor. So I have charged the capacitor and I am allowing it to discharge through an inductor and capacitor. Now I am focusing only on the discharge of capacitor through inductor and the resistor. At any point of time t, if I look at the current in the circuit, it will be I. I is the instantaneous current. And if I look for the charge in the circuit, the instantaneous charge will be Q. Charge on the capacitor at any point of time t is Q. Right. Now if I write an EMF equation, so VL is the potential across the inductor, VR is the potential across the resistor, and VC is the potential across the capacitor. So you have to write VL plus VR plus VC, which has to be equal to 0 because this is discharging. I am discharging the capacitor. So for discharging, you don't need any external source. You don't need any battery. You don't need any EMF. Therefore, I am not at all writing an EMF in the right hand side. So EMF is 0. While charging, you should compulsorily mention the EMF in the right hand side. But this is the case of discharging. You have to put 0 instead of EMF. Okay. Right. Now we know from the equations that we have been done this. We have been substituting for the potential the same equations. So VL is equal to L into di by dt, which is the equation for potential across inductor. And VR is equal to I into R, which is from the very famous Ohm's law. And VC is equal to Q by C. You know the potential across the capacitor. We use an equation. We have been using this equation. It is Q by C. Right. So I have substituted for VL, VR, VC, and I have equated this to 0 because I am looking for the discharging of capacitor. No source of EMF. So E is 0. Now I am substituting the current I as dq by dt. I know the current which is flowing through the circuit is the rate of flow of charge. So I is dq by dt. So therefore I substitute this I as dq by dt. Now this equation becomes L into di by dt becomes d square q by dt square plus I is dq by dt into R plus q by c is equal to 0. Now my equation is modified because I substituted I as dq by dt. Now what I'll do is I'll divide entire equation by L. If I do that, if I divide that equation by capital L, means the inductance, then our equation becomes d square q by dt square plus R by L into dq by dt plus q by LC, which is equals to 0. Now this equation can be written as, d square q by dt square plus, instead of R by L, I am writing 2b. I am writing some constant 2b instead of R by L. And plus, instead of 1 by LC, I am writing k square. I am writing two constants. One is b, another one is k. So 2b is what R by L and k square is what 1 by LC. Why I am writing in this form is because this is a standard form of the differential equation where I know the solution of it. Instead of taking this R by L and 1 by LC, I am writing it in a standard form in terms of b and k square, so that the solution of this is already known to me. Okay, right. So first we will see what is b and k square is. I told you that 2b is R by L and k square is 1 by LC, where b is R by 2L. So these are the two constants which I am introducing now. This b is one constant which is R by 2L and k square is another constant which is 1 by LC. So therefore I am substituting and I modified that equation and that becomes equation 1. You know that equation 1 represents a damped LC oscillation and solution of that above equation is known. It is a standard differential equation where the solution of that standard differential equation is simply Q is equal to A into e to the power of alpha t. Okay, writing an differential equation in a standard form where the solution is already known, and from the known solution I am setting up another equation, and from that I am evaluating the value of constant. Now I am writing after that I am writing a complete solution. That is a technique. Okay, yeah, I will go step by step, you will understand it clearly. Now I got a solution. I know the solution. Q is equal to A into e to the power of alpha t. Okay. Now what is A again? What is alpha again? Now these are the two again constants, and those values has to be evaluated, has to be found out, okay, by solving this. How to solve this? I'll go step by step. So if I write dq by dt, if I differentiate with respect to time once, dq by dt becomes a into alpha e to the power of alpha t. If I differentiate right hand side, it is a into e to the power of alpha t. Differentiation is alpha e to the power of alpha t. Okay. Now this becomes a into alpha e to the power of alpha t. Again I am differentiating this equation once again with time. Now this becomes d square q by dt square, which is equal to another alpha will get added here. So a alpha square e to the power of alpha t. Right. So I got dq by dt, and I got d square q by dt square, where these things I am going to substitute back in the equation 1. I know equation 1. So let me go back and see what is equation 1 is. So we have d square q by dt square plus 2b dq by dt plus k square q is equal to 0. I am going to substitute d square q by dt square and dq by dt in this equation 1. Yeah. So on substituting d square q by dt square, which is a alpha square e to the power of alpha t, plus 2b dq by dt is a alpha e to the power of alpha t, plus k square into q. Q also I can substitute, which is a e to the power of alpha t. I have substituted d square q by dt square in the first term, and I have substituted dq by dt in the second term, and I have substituted q in the third term. Okay, all I have substituted. There is no q term here. I have substituted everything. Now if I simplify that, I'll take this a e to the power of alpha t as a common factor, which is not 0. Therefore this alpha square plus 2b alpha plus k square is equal to 0. Okay, right, I got an equation 2. Let's call it as an equation 2, because number has got interchanged. You please make it as an equation 2. It is alpha square plus 2b alpha plus k square. Still one question is still in the mind, that I need to find the value of a and alpha. What is a and alpha? Because these are the new terms which I included directly in a solution of this equation. I need to tell what is actually the a and what is actually the alpha. These are the new terms. Let me find it out. Let me find it out with the help of this equation. Now I got equation 2, and solution of the equation 2, it's a quadratic equation whose solution is minus b plus or minus root of b square minus 4ac by 2a. This is a standard solution. You all know this in the mathematics. I am applying the same thing here, which is minus b. What is b over here? B is 2b. So minus 2b plus or minus root of b square. B is 2b here. B square is 2b square, which is 4b square, minus 4ac. A is 1. 4 into a into 1. Okay. K square. Instead it has to be 4k square. You please make the correction and make it 4k square. It is not just k square. It has to be 4k square. It is 4ac. 4, a is 1 and c is k square. It is 4k square. You please correct it. Divided by 2a. 2 is okay. A is 1. So it is divided by 2. Now I have written alpha. So alpha has to get two values here, because one is plus, another one is minus. So alpha, I can say one as alpha 1, another one as alpha 2. Instead I am expecting one solution, one alpha, but see I am getting two alphas here. One is alpha 1, another one is alpha 2. Sometimes some quadratic equation, when you are going to solve it, you will get two solutions. So these are the two solutions which I am getting, which is suitable for that quadratic equation. So alpha 1 is minus b plus root of b square minus k square, and alpha 2 is minus b minus root of b square minus k square. Now after knowing alpha 2, I can write a solution q as a into e to the power of alpha t. Instead of alpha t, I can write it as alpha 1t plus e to the power of alpha 2t, because I am getting the two solutions. So instead it has to be b. It is not simply a e to the power of alpha 1t plus b e to the power of alpha 2t. Please include b in this equation. So it has to be b e to the power of alpha t. You please correct it. So it is b e to the power of alpha 2t. Now you know what is alpha 1 is and alpha 2 is. If you substitute alpha 1 and alpha 2, you will get a big equation. Q is equal to a e to the power of minus b plus root of b square minus k square into t plus b e to the power of minus b minus root of b square minus k square into t. Right, I got a big equation for Q. So similarly you find an equation for current as well. What is actually the current? It is rate of flow of charge. It is first order differentiation of charge. It is dq by dt. If I differentiate that, so a, whatever the coefficient of t, I will write it here, minus b plus root of b square minus k square into e to the power of minus b plus root of b square minus k square into t. Okay, again differentiate this second term plus b. Write then the coefficient of time here, minus b minus root of b square minus k square e to the power of minus b minus root of b square minus k square into t. T is there but it is missing here. Okay, you please write the t over there. So if you differentiate that charge equation, you will get the current equation. Simple thing. Maybe it looks big. The equation looks big, but it's a very simple equation. If you differentiate the charge, you will get the equation of current. Now what I will do is I will evaluate the values of constants a and b. It is not simply a, we have some more constant added here, b. No, I need to find the value of a and b. Okay, I'll apply one initial condition. At time t is equal to 0, I am doing discharging. It is a discharging of LCR circuit. While discharging, while at time t is equal to 0, what will be the charge on the capacitor? The capacitor will be having a maximum charge at time t equals to 0. Initially, while discharging, charge on the capacitor is full, it's maximum. So therefore, at time t equals to 0, Q equals to Q naught. It is a maximum charge. So therefore, if I substitute this in the charge equation, the earlier equation, the first equation, Q equals to what you have to substitute? Instead of Q, I have to substitute Q naught A e to the power of something into 0. E to the power of 0 is 1 plus b into again e to the power of 0, which is again 1. So a plus b. So a plus b is equal to Q naught. I am substituting this t equals 0, Q is equal to 0, Q naught in a charge equation. So I am getting a plus b as Q naught. Next, I am applying another one condition, that is at t is equal to 0, I am looking for the current. Look at the current. Current is rate of flow of charge. It is dq naught by dt. Again, it is also 0. So how this current is 0? At time t is equal to 0, I can say that the charge on the capacitor is constant. It is maximum value, and it is constant, peak value. If you differentiate a constant, you will get 0. So current will be 0 because charge is constant and it is maximum at time t is equal to 0. So obviously current will be 0. Now take that big equation, current equation. Substitute this condition, t equals to 0, I equals to 0 there. I 0, right, I can write it left hand side. A into, I'll get minus b root of b square minus k square into 1 plus b into minus b minus root of b square minus k square into 1. I'll take out minus b one side and root of b square minus k square on the other side. If I take a plus b minus b as a common factor, I'll get a plus b. If I take root of b square minus k square as a common factor, I'll get a minus b. Right. So after getting this, I'll make a rearrangement and I'll substitute for a plus b, which I just found out that it is q naught. So a plus b is q naught. I'm substituting it in this equation. So our a minus b will be equals to b q naught divided by root of b square minus k square. Okay. You simply solve this equation. Solve means it simply rearrange this equation and substitute for a plus b. I'm talking about last equation. In the last equation, just substitute for a plus b as q naught and rearrange, you will get a minus b. Once you get a minus b and a plus b, it is easy for us to calculate a and b separately. Add these two, you will get a. Subtract these two, you will get b. From subtraction, you will get a. Addition, you will get b. Do that. If you add and if you subtract, you will get the value of the constants a and b separately, which was presented in the PPT. Q naught by 2 into 1 plus b by root of b square minus k square, and the b is q naught by 2 1 minus b by root of b square minus k square. Now you go back to the charge equation and substitute for a and b. You will get a complete equation. You will get a very big equation after substituting a and b in the charge equation. This is what the final equation. This is what the equation which I was trying to derive, because I am deriving the charge equation during discharging of the capacitor through L and R. I got this equation. So now there is no constants here. All constant has been evaluated and all constant has been substituted, and I have substituted for a and b as well. Now you don't find any constants here. Only thing is you are finding some b and k. I have defined what is b and what is k earlier itself. Okay. Now you don't find any new terms, any new constants. All the constants has been evaluated and substituted back in this equation. I got the final equation. This is the final equation for the charge on the capacitor at any instant of time t. Earlier, while doing CR circuit, charging and discharging, I used to get a very small equation. But this is a complex equation because this LCR circuit itself is a complicated thing, because 3 components are there. So that is why I am getting a very complex equation. Anyhow, I have derived an equation for the charge on the capacitor during discharging of the capacitor through inductor and the capacitor. After getting the final equations, I have still some more thing to discuss. I have 3 cases left over to discuss here. Case 1, if b square is greater than k square. You know what is b square is. B square, as I defined earlier, it is r square by 4l square, and k square is 1 by lc. If that is the case, if r square by 4l square is greater than 1 by lc, in this case, you look for how charge is decreasing. The graph which is beside this will clearly shows you how the charge is decreasing in the capacitor. So charge decreases slowly. You look at the graph, when time proceeds, charge is very slowly decreasing. In this case, in the first case, charge will decrease very slowly. Exponentially, yeah, but exponentially. Charge will decrease exponentially but very slowly in the first case. When we look for the second case, if b square is equal to k square, I mean to say r square by 4l square is equal to 1 by lc, and r square is equal to 4l by c. If that is the case, the charge will decrease exponentially but little more quickly compared to the case 1. It decreases quickly to 0. Such discharge is called critical damping. Okay. In the second case, if b square is equal to k square, the charge on the capacitor decreases quickly to 0, and this is called critical damping. Here we have still one more case left over, which is b square less than k square. I mean to say r square by 4l square less than 1 by lc. On substituting in the main equation, if I substitute this in the main equation, which I got a very complex equation for the charge, I finally, after simplification, I'll get q equals to a cos omega t. This equation will tells you that the charge will decrease. It follows the cos theta. It's a cos wave. Charge decrease is a cos wave, and the decrease is oscillatory in fact. The decrease is oscillatory, which was shown in the graph in the right hand side. Okay, so charge will come down to the negative axis, then go to positive axis, then come to negative axis. It starts oscillating and finally reaches to 0. This is the third case. First, second and third case, if all these three cases, if I want me to show in a one single graph, look at the last graph. Look at the last, which is in the bottom right corner, where I have mentioned all the three cases. The case A, where the charge decreases slowly but exponentially. This is what the case A. In the graph B, the charge will decreases fast but exponentially. Again, exponentially is followed here. Look at the graph C. In the graph C, the charge is oscillatory. Charge will decrease like an oscillatory function. Okay. So I have explained all the different three cases by taking the very complex equation for the charge. This completes the discharge of the capacitor through an inductor and the capacitor. Okay. Yeah. Thank you very much.